There are situations where you want to control the position of an emitter while maintaining the behaviors of a scatterer or managing a multitude of emitters sharing the same sound. The alternative to manual positioning or actor inheritance is to provide the meshes with an atomic component capable of determining its position and ownership tag, which can then be associated with its biome emitter at runtime once certain conditions are met. The biome point tag is a lean atomic component that, as asset user data, can be inserted into static meshes and allows the mesh's position to be recorded within a hash grid. Once saved within the mesh and positioned in the level, the hashmap bake command saves the hash grid to an overwritable and editable data asset. The runtime subsystem manages instance queries with a loose octree method, eliminating the cost of full scene search. Biome point mode allows you to use points baked with the biome point tag, allowing for precise positioning on meshes of any scale. By using a socket connected to the asset user data, you can provide an offset from the mesh pivot point, allowing you to work with large or irregular objects. If you don't set a socket, the default coordinate is the mesh pivot point. In the biome element definition, simply list the biome point tag you want to connect. And at runtime, you will see the biome emitter position itself at the precise point set in the editor. The voice budget is always managed by voice manager tokens. A nearest candidate list is established as the internal priority order, and a density check is then performed, favoring the closest biome point tag for each request. The density check instead makes sure that the same point cannot be claimed by two identical emitters. The combination of these emitters modes and the scalability offered by its parameters allows for an efficient system capable of delivering rich sounds. For example, within this sandbox, 10 emitters are used for a total of 75 biome point tags, ensuring a significantly lower cost compared to manual placement or actor inheritance, since each emitter is promptly recycled and the total number of actors present is reduced. In the next video, we'll explore the possibilities of collecting parameters in the subsystem and applying heuristics for real-time modifications, using a dynamic weather system as an example. That's all for today. Thank you for watching. Seeing you next time.